Hey, what's up, my chemistry people? It is going to be a thriller of a video. What in the heck are we gonna do? We're going to make qualitative or quantitative predictions about redox reactions based on half-cell reactions and potentials, and analyze these cells to identify properties of the underlying redox reactions. Woo! Now, specifically in this vid, we're gonna look at balancing a redox reaction in acidic or basic solutions using the half reaction method. It's a doozy, so stay in your seats. I know it's gonna be thrilling. So, turns out that many redox reactions occur in acidic or basic solutions. The steps to balance are very similar to balancing redox reactions in just regular aqueous solutions, but we have to account for the hydrogen ions and hydroxide ions that we see in acidic or basic solutions, respectively. So, 4 big steps. First, balance elements other than hydrogen and oxygen. Second, when you need to balance the oxygen, you're gonna add water to do that. Third, if you're in an acidic solution, you're gonna add hydrogen ion where hydrogen is needed to be balanced. And this is possible because in an acidic solution, we've got a bunch of extra hydrogen ion just floating around. Now, if you're in an acidic solution, you're done. But if you're in a basic solution, you've got one more step. And that step is to add hydroxide ion, neutralize that hydrogen ion, and correctly depict the fact that we're working in a basic solution. Okay, so let's first look at an example of balancing a redox reaction in acidic solutions. We're gonna use this exciting reaction between iron 2 and permanganate ion occurring in acidic solution to practice balancing by half reaction method. First thing, assign oxidation states to each element in the reaction to determine the element oxidized and the element reduced. +2, -2, +7, +3, +2. Next, write oxidation and reduction half reactions, including the electrons. Also good practice to include the oxidation and reduction potentials for each of those half reactions. Keep in mind, oxidation half reactions will have electrons on the right, reduction half reactions will have electrons on the left. Don't forget, you're often working from a reduction potential chart, so keep in mind that when you're writing down the oxidation potential, same value but opposite sign. This sucker's being oxidized, going from +2 to +3. Boom! Oxidation half reaction. As I check my reduction potential list, my oxidation potential, same value, opposite sign. Boom! Oxidation half reaction. The manganese in the permanganate ion goes from +7 to +2. Boom! Reduction half reaction. As you think about the number of electrons that you're including here, just think about the oxidation states. In order for the manganese to go from +7 to +2, it must have gained 5 electrons. My reduction potential for the permanganate ion in acidic solution, positive 1.51 volts. Boom! Reduction half reaction. Step 3. Balance each half reaction for mass. You're first going to balance elements other than hydrogen and oxygen. When you need to balance oxygen, add water, and then finally add hydrogen ion to balance the hydrogen. As I look to balance for mass in the oxidation half reaction, notice that I have 1 iron on the reactant side, 1 on the product side, already balanced for mass. As I look at the reduction half reaction, I've got 1 manganese on the reactant side, 1 on the product side, but I have 4 oxygen on the reactant side. To balance oxygen, I'm going to add 4 waters. So although I've now balanced for oxygen, I now need to balance for hydrogen. To balance for hydrogen, you add hydrogen ion. And again, because this is happening in acidic medium, we've got a bunch of extra hydrogens around to help us do that. Finally, it's important that you also balance for charge between the half reactions. You've got to make sure that the number of electrons gained in the reduction half reaction are equal to the number of electrons lost in the oxidation half reaction. But importantly, and this is a common error, those oxidation and reduction potentials are intensive. They stay the same. So if you are going to multiply a half reaction by a factor, don't multiply the potentials. Alright, now that my oxidation and reduction half reactions are balanced for mass, as we look carefully at these 2 half reactions, notice that my oxidation half reaction shows iron 2 losing 1 electron, but the permanganate ion gaining 5. So I need to multiply this half reaction by a factor of 5. I'm not going to multiply my oxidation potential. Boom. Now I'm showing 5 electrons lost, 5 electrons gained. And then finally, recombine the half reactions into one complete overall reaction, canceling out the electrons and adding the potentials. Our final step here is to recombine the equations. As I look to do that, I can cancel out the electrons and they won't show up in my overall reaction. Anything else that's on the left-hand side of one equation and the right-hand side of another would also cancel out. Then you just sum the equations together. Boom, here's my balanced overall equation in acidic solution. Final thing we want to do is determine the cell potential for this overall reaction. To do that, we simply add together the reduction potential and the oxidation potential to get positive 0.74 volts, indicating we've got a thermodynamically favorable reaction. Alright, now let's take a look at balancing in basic conditions. The process is really similar, just one added step. Alright, let's take a look at this reaction between iodide ion and permanganate ion in basic solution as an example to balance a reaction occurring in basic solution. Once again, we're going to assign oxidation states to each element in the reaction. Determine what's being oxidized, what's being reduced. -1, -2, +7, 0, -2, +4. Again, write oxidation and reduction half reactions, including electrons. Don't forget the reduction and oxidation potentials. Remember, those oxidation half reactions will have electrons on the right, reduction half reactions will have those electrons on the left, and then don't forget, common mistake, when you're pulling from a reduction potential chart, the oxidation potential, same value but opposite sign. I'm going to take a look at my iodide. It goes from -1 to 0, indicating that it has been oxidized. Now, I'll do this example a different way, where initially I'll leave the electrons out. So if you're having a hard time trying to figure out how many electrons to include, this way might be a little easier. Boom, here's my oxidation half reaction. Again, as I check oxidation states, the manganese in permanganate ion goes from +7 to +4, indicating that it's been reduced. So my reduction half reaction, boom, reduction. Step 3, really similar. First, balance elements other than hydrogen and oxygen. Second, add water to balance out the oxygens needed. Third, you're still going to add hydrogen ion where hydrogen is needed. But here's the important difference for basic conditions. Once you've balanced out the hydrogen and oxygen, you need to neutralize those hydrogens with hydroxide, and you'll add the same number of hydroxides to each side of the equation. These steps are just the convention we work through to balance the equation, and ultimately we have to show the reaction is taking place in basic conditions. All right, next, let's balance for mass. I've got 1 iodine on the left, 2 on the right. A 2 will balance my iodines. For the reduction half reaction, manganese are already balanced. My oxygen are unbalanced. First thing I'm going to do is add waters to balance out my oxygen. Then I'm going to add hydrogen ion to balance out my hydrogen. But this is happening in basic solution. So what we're going to do is add the same number of hydroxide ions as hydrogen ions to neutralize them on this side, and just make sure to add them to the other side as well. Again, the step-by-step method is just a convention that we use for balancing it. So if you're confused, just practice the steps. Again, it's just a method to come up with the balanced equation. So what does that do for us? Well, the 4 hydroxide and 4 hydrogen ion will form 4 waters, and we'll be left with a reaction occurring in a basic solution. Okay, now we need to balance for charge. Now remember, this time I left the electrons out originally. Here's where we're going to add them back in. As I look at the left-hand side of my oxidation half reaction, the total amount of charge on the left-hand side is -2, because each of those iodide ions is contributing -1 charge. On the right-hand side, there's nothing charged, so it's 0 over here. I need to balance the charge within the oxidation half reaction. In order to do that, we're going to add electrons. And in oxidation, we'll add them to the right-hand side. As I look at my reduction half reaction, the total charge of things on the left-hand side is -1. On the right-hand side, it's -4, because I have 4 negatively charged hydroxide ions. So, to balance out the charge within the reduction half reaction, I need to add 3 additional electrons. Now the total charge on the left-hand side is -4, and on the right-hand side is also -4. So if you have a hard time figuring out what's going on based on oxidation numbers, sometimes it's easier just to wait until after you've balanced for mass to add those electrons in. Step 4. Again, balance charge. So important that the electrons lost equal the electrons gained. We've lost 2 electrons in our oxidation half reaction, but gained 3 in our reduction half reaction. So I'm going to multiply my oxidation half reaction by a factor of 3, my reduction half reaction by a factor of 2. What results then is an oxidation half reaction and reduction half reaction that are losing and gaining equal numbers of electrons. And then finally, recombine, add those potentials together. Now before I sum my equations together, I'm going to cancel some things out. Electrons, 6 electrons gained, 6 electrons lost. I can also cancel out some waters. I've got 4 waters on the product side, 8 on the reactant side. So I can cancel it out, so there's only 4 on the reactant side. Again, you can cancel out anything that is on the reactant side and also on the product side. All right, let's sum these together. Whew, that's a doozy. But notice now we have a correctly balanced redox reaction that's occurring in basic solution. That's it for this video. I know it was a thriller. Totally understand if you need to watch it again because it was just so exciting.